Thank you very much for the kind introduction. I would first like to thank the organizers for such a very great event, and of course for kindly giving me the opportunity to give this seminar. So I'm very happy to give this talk, which is in collaboration with Michael Weinstein from Columbia University, and it's about honeycomb structures in non-commensurate edges. So the overall motivation of this work is to study wave propagation in graphene, which is represented here on the left. So graphene is a two-dimensional honeycomb arrangement of carbon atoms, and it was first experimentally isolated in 2004. So since then, graphene has attracted a lot of interest in the applied community, but also in the mathematics community, and it has led to the creation of many variants in acoustics, photonics, or even in optics, which are called graphene-like systems. So one of the many interesting properties of graphene is its ability to support edge states. So edge states are, formally speaking, solutions to a conservative wave equation that propagates in the direction of the interface, separating two distinct structures, and then decays in the transverse directions. So one thing which is quite interesting, especially with graphene, is that in some identified settings, it has been shown that these edge states persist even under perturbations of the interface. So you can see this with this numerical simulation. I can bend the interface, or I can even add some sort of randomness, and the state kind of just propagates along the defect somehow. So this phenomenon has been explored from a mathematical perspective using topological arguments for discrete models or for Dirac models. And here what I'm going to do is something a little bit different. I'm going to consider a continuum honeycomb Schrödinger operator instead. Okay. So in what follows, I'm going to describe how we generate the model. But first, the starting point is going to be the Schrödinger operator minus Laplacian plus V, where V is periodic with respect to a lattice, a Bravais lattice, with associated dual lattice lambda star, so on the top there. So an example which will be central to this analysis is going to be the equilateral triangular lattice, which is represented on the left there. So because V is periodic with respect to the lattice, one can show that our operator H0 commutes with translations along the lattice as well, and therefore it leaves the space L2K invariant. So L2K is the space of functions which are equal to their translations along the lattice modulo a phase shift. And that phase depends here on a parameter K, which is called the quasi-momentum. So in particular, one can show that whenever I shift my quasi-momentum along the dual lattice, K1 or K2, I recover the same space, therefore the same operator. So I can restrict K to a unit periodicity cell. So you see that in particular, I can restrict H0 on L2K, and that gives me H0 of K, which is self-adjoint with compact resolvents, and therefore its spectrum consists of eigenvalues here labeled E1, E2, and so on, which tend to infinity with associated eigenfunctions which form an orthonormal basis of L2K. So a little bit of terminology. Of course, I can map K, the quasi-momentum, to the eigenvalues, and when I do that, I have something called dispersion functions, and the graphs of these functions are called dispersion surfaces. One can also show that these dispersion functions are Lipschitz continuous, and because they are periodic, their image is a compact set, which is called a band. And finally, a consequence of Floquet-Bloch theory is that the union of all the bands forms the spectrum of H0. So this is kind of a very general, very quick introduction to these operators with periodic potentials. Now I'm going to restrict myself to graphene, which is a particular periodic potential. So in order to mimic the symmetries present in graphene, I'm going to assume some additional information, so particular here called symmetries. More precisely, I'm going to assume that V is inversion symmetric, meaning that V of minus x is equal to V of x. And then I'm going to assume that V is also real valued, or also said invariant under complex conjugations. And finally, I will assume that if I rotate V by 120 degrees clockwise, I get the same potential. And the simplest example you can think of, but also physically relevant, is to imagine a cutoff function, which is a radially cutoff function, and its translates, which are on these purple spots. So if you were here last week, Peter Cushman gives us a very nice talk where he presented some properties regarding analyticity, for example, of the bands, properties that are expected to hold generically. And it turns out that for these potentials, which represents graphene, they don't always hold. And that's what makes graphene so interesting to study. More precisely, let me represent here the dispersion surfaces. So you see that on the x-axis, I have the vector k, the quasi-momentum, and on the y-axis, I have the spectral parameter, which is here. I will refer to it as the energy. Okay? And so here I have plotted two consecutive dispersion surfaces, and something that is quite interesting is that you see that they touch at points. And this is represented here by saying that, so the point k star ed is such that ed is a double eigenvalue of my operator. And moreover, when we blow up the dispersion surfaces, we see that the intersection is conical, and that's represented here by this expansion on the right. So there are many names for such points. I believe they were called at some points the devil's points or something like that. Diabolical points, thank you. Yes. So I will choose here a more neutral name, and I will just call them Dirac points. Okay, thank you very much. Thank you. Thanks very much. Okay, it's not, okay, okay, thank you very much. Thank you. Okay. So yes, these Dirac points for the honeycomb Schrödinger operator have been shown to occur generically, so within the class of honeycomb lattice potentials. And they occur for these particular types of vertices K star, which are also referred to as high symmetry quasi-momenta. So for people who are familiar, these are precisely the vertices of the Brillouin zone. So what is quite interesting with these Dirac points is that, you see, if I take a wave packet which is spectrally localized near these points, and I were to solve the Schrödinger equation in time with an initial data, which is that wave packets, then the dynamics are going to be governed by an effective Dirac operator, rather than, for example, I don't know, a transport operator or something else. Moreover, what is quite interesting also is that these Dirac points, they are very robust when we choose a perturbation which preserves parity symmetry and conjugation symmetry. But as soon as you break one of these symmetry, you completely destroy the Dirac points. And one way to do that is to take a sheet of graphene and to impose a magnetic field in the perpendicular direction. And that can be here modeled by adding this term here, which is also called a magneto-optic term, where you see that the function a of x is periodic with respect to the lattice. It's also even and real valued. However, sigma 2 is purely imaginary because it's the second Pauli matrix, and therefore this perturbation right here completely breaks invariance under complex conjugation. So for that reason, what happens is that generically, the dispersion surfaces become smooth near the Dirac points, and a local gap of size delta opens there. So now the model, I'm actually interested in situations where we take such a sheet of graphene, say H plus delta on one side, H minus delta on the other side, and we try to connect them along an interface. So here my H delta minus will be the blue one, and H plus delta will be the red one. And the interpolation here will be encoded by adding a term here, which is a domain wall, and that is the function kappa. So you see, it's now, we have added this term right here, which is kappa. So kappa is a function of one variable that tends to +1 or -1 in plus or minus infinity. So in particular, you see that when kappa is equal to -1, we recover the operator asymptotically far from the interface, but when kappa is equal to +1, we recover the red one. However, kappa is smooth. This is not a sharp junction as one would be used to in photonics, for example, which is why you see these kind of gradients in color between the red and the blue ones. And finally, we see that the interpolation happens in the direction transverse to an edge, which here is given by v hat, and v hat is a combination of v1 and v2, which features a parameter r. So in particular, I will say that the edge is commensurate or rational if r is a rational number. Otherwise, I will say that the edge is non-commensurate or irrational. Okay, so now my interest here is to study the spectral properties of my Hamiltonian. Okay, I want to study the spectral types of these operators. And right off the bat, one thing that can be very easy to show is that if I look at the spectra of my asymptotic operators H delta plus and H delta minus, they are both contained in the spectrum of the edge operator. However, the converse is not true. So more precisely, the spectrum of H delta has an additional component, which is called here spectral edge informally, and the nature of the spectrum in general is not known. So intuitively, what we imagine is that this is a spectrum that corresponds to solutions which are going to be, you see, for example, bounded in the direction of the edge, and perhaps they decay in the transverse direction. And this is what is called, in general, edge states. They open on the both sides. And then now that you join these two materials, you cannot even talk about dispersion surfaces anymore because you don't have periodicity in general. So of course, one may be interested in whether these edge states exist and also what is their behavior in the direction of the edge. And here, the fact that the edge is commensurate or not is going to play a very important role. More precisely, when you have commensurate edges, it turns out that your medium, as you can see, is periodic in the direction of the edge. And so that means that I can use Floquet block analysis again and define here my edge states as solutions which equal their translation along the interface modulo a phase shift. And that phase shift, I will call it here the parallel quasi-momentum. So this operator right here, of course, is defined on an infinite domain. So it isn't compact resolvent. It can have continuous spectrum, but it does have point spectrum as well. So in particular, if I look at this operator, one shows that, or it has been shown 10 years ago, and it was one of the first results for these types of models, that when I take rational edges and I take delta small enough, then my operator has eigenpairs. And these eigenpairs bifurcate from the Dirac points. So they are kind of seeded by these Dirac points in particular. So here is a picture which represents what they look like. You see that in the x-axis, I have represented the parallel quasi-momentum. So if you fix one value of that, you get a gray area which corresponds to the continuum spectrum. But then you have these red points, for example, which will correspond to an eigenvalue, discrete spectrum. And those are precisely the edge states. They correspond to the edge states. Now you can kind of project the spectrum or take their union over K parallel, and what you get is the spectrum of the full operator. And you see that we have a gray area which corresponds to the states that are propagating in all directions. And then we have also some edge spectrum, which can also, of course, is not disjoint with the gray one. and that corresponds to the edge states in particular. So now, when one presents such works, that's what I've usually seen. The natural first question one asks at the end is, what happens for non-commensurate edges? And that's precisely the case I have looked at with Michael Weinstein. So, sorry, yes, please. Yes.
Is it always the case that these edge states will fill out the gap between
No.
Oh, okay.
For this model, near the Dirac energy, it's true. But if you take an arbitrary rational edge for arbitrary periodic operators, no. You can still have gaps for rational edges. But for non-commensurate edges, it's no longer true, actually. So more precisely, it turns out that you can show in that case that all the bulk gaps gets completely filled with edge spectrum. So there are no more gaps. There are never gaps. Okay. And it's very interesting because so the papers that were shown, used to show these results, are very short papers with very elegant proofs relying on either variational arguments or topological arguments. And of course, one would be interested in knowing the proper nature of this spectrum. And for example, in my first publication with Michael, it took us at least 80 pages. So probably it's because, you know, I'm a noob and maybe I'm not very good at writing a paper, but it's also because understanding the nature of these spectra is fundamentally more complicated than anything. Okay. Moreover, it has been shown as well that for discrete models, you can actually show that the spectrum that fills the gap has an absolutely continuous part, but of course there could be other things there. You could have eigenvalues sitting there. You could have singularly continuous spectrum. And so what makes this problem more complicated than in the rational case is that you no longer have periodicity along the edge, so you can no longer use adapted tools such as Floquet block transform. And the idea we used there was actually that if you follow the medium in the direction of the edge, even though you don't have periodicity, you have something which is called quasi-periodicity. More precisely, one can write my medium as the restriction of a higher dimensional medium along a certain line. So think, for example, of cosine of x plus cosine of x square root of 2. Those are the types of behavior happening along the interface. Okay. So the idea was to kind of use that quasi-periodic nature and compute and study these edge states. And this, for this particular type of media, is something that was used a lot in the world of the homogenization theory, but a bit less for spectral problems or for diffraction problems, which is the ones I'm interested in here. Okay. So I'm going to explain how to obtain this quasi-periodicity. There are many ways to do it. You can do it. There is a very geometric proof to this. I'm going to use a more maybe physically motivated proof, which is by introducing dislocations of this operator. Namely, you see that now I add an additional parameter, which is the S variable here, and that's within the domain wall. So what happens when I move S? When I move S, so when I move S, you see that the edge is going to move as well. And of course, the value of the medium changes as well. So in general, when you have rational edges, you can study these dislocations independently from one another, and that can give you a lot of information on the edges. It can tell you whether, for example, the edge states are topologically protected, or it can give you information also on the speed at which these edge states propagate, their group velocity, more precisely. Of course, here they are all going to be coupled in the irrational case, and what we want to do is basically to study these dislocations collectively by treating S as a new variable rather than a parameter. So what that means is I'm going to introduce the following operator, which is exactly the same as before, but now you see that it acts on L2 of R3. So S now plays the role of a variable rather than a parameter. And of course, I have replaced my gradients with partial gradients in X. So I'm going to talk a lot about the properties of this operator in the sequel. But first, I wanted to show the type of mediums that would be represented by this potential. So here is my poor, humble attempt at trying to represent that. So in other words, this three-dimensional medium is kind of an extrusion, if you want, of the two-dimensional one. Okay. So in particular, S, my additional variable, is the vertical one here. And if I take my slice at S equal to 0, I recover my original medium. Okay, so for S equal to 0, we have the original material. Moreover, you can see that from the definition of this operator, actually this is also a junction or a dislocation between two different periodic materials. And this happens in the direction transverse to a certain two-dimensional interface, which is why you see that the cylinders, I don't know if it's shown here properly, but you can see that the cylinders, they get redder when we are far from the interface or bluer when we are, for example, below the interface. And now finally, if I were to look at my medium in the direction of this interface, remember the two-dimensional medium isn't periodic. However, this one sees clearly that it has some periodicity along two vectors, A1 and A2, which are given by this expression. Okay. So here the idea is that in order to recover periodicity, we have lifted our operator in higher dimensions somehow. So the natural thing, once we have done that, is this is the definition for our edge states in 2D. So because our medium is the restriction of a higher dimensional medium along the line, along a plane, of course, it's natural to try to look for our edge states also as the restriction of an edge state in 3D now, where these edge states satisfies the following eigenvalue problem and decays in the transverse direction, which here would be S. Moreover, you see that since my augmented medium also satisfies the following translation invariance properties, I can use that and look for edge states which satisfy the following pseudo-periodic boundary conditions, which now feature two parameters, k parallel and k naught. So it turns out that I can actually choose k naught to be 0, for simplicity, I will do so. So here we require that we just have periodicity in one direction. Okay. And so that leads us to having the following operator. So we can now define augmented edge states as non-trivial solutions to an eigenvalue equation or eigenfunctions of the following operator, which acts on a space of 3 variables, which have the following pseudo-periodic boundary conditions and then decay in the transverse direction. So in particular, functions that live in this space are now in a 3-dimensional cylinder, if you want. Okay. So the idea is that if you're able to find eigenfunctions that are like this, and if they are continuous with respect to s equal to 0, of course we can take the slice at s equal to 0 and then we would have a proper 2-dimensional edge state. It turns out that, formally speaking, when you do this for rational edges, you recover precisely the behavior for rational edges, so it's expected. But then when you have something which is non-commensurate, you get a more complicated behavior, which is here a quasi-periodic behavior. Okay. So far, so good. But you see, by doing this, I have somehow transferred the difficulty, because you see that the augmented operator has no derivative in S. So this isn't your typical Laplacian, for example. And for that reason, the spectral properties of this operator are extremely different from the ones of the classical Schrödinger operator. So one way to view this already is, you see that if I shift, so this operator depends on k parallel through its domain. So if I move k parallel by 2 pi, I get exactly the same thing, which is what the first relation gives us. However, you see that because we don't have any derivative in S, when I multiply my operator or when I conjugate it with any function which depends on S, it doesn't change the differential expression here. So the only thing it changes is going to be the domain or the space on which it acts, and one can show that it's equivalent to shifting k parallel by 2 pi r. So what does this mean for the spectra? It means that the spectrum as a function of k parallel is both 2 pi periodic and 2 pi r periodic. Moreover, it's continuous in some sense, and you have a continuous function which is periodic with non-commensurate periods. It has to be constant. So as a consequence, the spectrum is independent of k parallel. So this is very different from what you would expect typically for rational edges, once again. But it doesn't tell you anything about the eigenvalues of these operators, which are what we are interested in. And this is exactly the subject or the objects of our results. So I'm going to walk you through the results, but what we show is the following. We show that if you look at the Dirac energy, so that's where the Dirac point happens, you see that there exist two curves. There is a curve which is concentrated here, which is, located in a neighborhood of K. Capital K is the point where the Dirac points happen. It's a high symmetry quasi-momenta projected on the edge vector. And then we have also a red curve, which is here. So if you take, for example, one point of this curve, you get exactly an eigenvalue. Okay? Moreover, one can show that these edge state curves, so these are called edge state curves, they are Lipschitz continuous and they are monotone in K parallel, the parallel quasi-momentum. And one can show that the associated eigenfunctions decay exponentially in the transverse direction. So this is all in the 3-dimension. Okay, we are in the augmented dimension, but now one can also show that these augmented states are continuous in S. So that means that I can restrict them to S, and by doing this, I have 2-dimensional edge states. So I haven't written it here, but one can actually show that these 2-dimensional edge states are also complete near the Dirac energy. So in other words, this kind of lifting idea allows us to find all the possible edge states. So the main result normally is titled dense point spectrum, but I've only shown you here two curves. But you see, because we have these two relations, turns out that if we have an eigenvalue of my operator, I can shift that eigenvalue with any multiples of 2 pi or 2 pi r, and therefore I would get another eigenvalue as well. So in particular, because I know these two eigenvalues, you see, by just translating them, I get completely countable number of other eigenvalue curves which fill the gap. Okay? So in particular, if I fix one value of k parallel, I have a countable number of eigenvalues. So I have dense point spectrum for this operator. So for rational edges, you could do the same thing. You could also lift the problem and look at this operator. And there for some reasons, there are reasons to believe that this operator doesn't have eigenvalues. So in order to go from absence of eigenvalues to dense point spectrum, there is kind of a discontinuity in some sense which happened there. And in order to cope with that discontinuity, we have to make an important assumption, which is that my number R is not too close to rational numbers. Okay, so it doesn't mean anything because, of course, rationals are dense in the real numbers, but it will say something about the speed at which I can approximate my irrationals. So on top of that, I will have to make another condition, which is that the dispersion surfaces that touch at the Dirac point, they do so only at the high symmetry quasi-momenta. So this also, you can view it geometrically. It means that so the dispersion functions should not fold over the Dirac energy in some sense. And so this is not an empty condition. One can, for example, so this condition doesn't hold if v is equal to 0. So it's rather a restrictive condition. However, it turns out that in a regime called the strong binding regime, so if you take your potential to have a very large amplitude, then it will hold eventually. Yes, please. Oh, the R. So the R is the direction of the edge. Yes, it's the edge, yes. Please feel free to stop me if you have any question. So I'm going to make a quick summary. So if I want you to take something away from this talk is that I have introduced a class of honeycomb Schrödinger operators. And the idea is to use the fact that they are quasi-periodic along the edge, lift them in higher dimensions, and study a three-dimensional augmented problem. So using this kind of technique, we have been able to show that our augmented problem has dense point spectrum, and we can restrict the edge states to obtain original two-dimensional edge states. So now I'm going to present the proof of the theorem, but before I wanted to stop here in case anyone has question. So I just wanted to make sure first that the result seems okay and clear. It's a cut and project, yes. It's exactly that, yes. So it's we lift and then we take a cut after, exactly. Okay, can I? Okay. Yes.
It's going to fill the whole, it's going to be dense no matter what, right? So the point spectrum.
Yes, the point spectrum is going to be dense. So this Diophantine condition, it just tells you that, I will present it later, but it tells you just that they shouldn't accumulate too fast if you want. So you have in particular, it's also a statement on the irrationality measure of R for people who are familiar. This is assuming that the irrationality measure is finite. So typically Liouville numbers, which are you take sum of 10 to the power minus k factorial, this wouldn't satisfy those types of condition. So now I'm going to present the proof in the remaining time I have. It's a little bit technical, but I just want to convey the main ideas for this proof. So the first thing is we want to construct these augmented edge states. But in order to do that, we're going to use perturbation theory. So we first need to understand what we expect these edge states to look like. Okay. So in order to do this, I'm going to do a formal multiscale expansion, which is very used in homogenization theory, for example. Because you see, my operator involves two scales. Because delta is going to be small, it has a scale which is a slow scale related to the junction between the two materials. And then it has a fast scale which corresponds to the bulk medium. So a very natural thing I'm going to do here is to look for my augmented edge states. This is all formal, by the way, as a function which depends on the slow variable and on the fast variable. And then I'm going to expand that in powers of delta. More precisely, I look for my augmented edge states as this combination, so it's expanded in powers of delta, and you see that each of these terms depend on the fast variable and on the slow variable. More precisely, I also require them to be pseudo-periodic with respect to the fast variable, and then I require them to be decaying in the slow one. I do the same thing for the eigenvalue. Then I take this ansatz, substitute it in the PDE, try to solve it. I will get a cascade of equations. I try to solve them iteratively. So I won't do that with you because it's a little bit technical. But the thing that one shows is that at least at first orders, my augmented edge states looks like the following. It looks like a product of a function which depends on x and a function which depends on zeta, zeta being the slow variable. Okay? So the function which depends on x is going to be a vector valued function which contains phi 1 and phi 2, and you see that it's a solution of the following equation. So we can do this because remember the Dirac point's a double eigenvalue. So it has the eigenspace is of dimension 2, so I can always take two linearly independent vectors, and with those linearly independent vectors I can construct a phi k to obtain this quantity here. Moreover, on the other hand, alpha 0 combined with the value z0 here can be shown to be the eigenpair of an effective operator. So usually in classical homogenization theory, you obtain a cell problem. Here you obtain something a bit different. You obtain a Dirac operator. So this is a first order matrix valued operator, which involves in particular the domain wall kappa. Okay, so you can continue this to any arbitrary order, and by doing this, you obtain something that is an approximate eigenpair in the sense that if I were to cut my expansion and I were to plug this within the equation, I get something which is not 0, but it's approximately a big O of delta to some power, for example. So now that we want to construct genuine eigenpairs, the thing that we're going to do is to replace all the remaining with unknowns. More precisely, I'm going to look for my eigenpair as my ansatz plus something which is unknown here, capital U, and here tau, where we will try to determine U and tau. Okay. So you take this and you substitute it again in the equation, and of course what we obtain is that my corrector pair satisfies now a PDE with a second right-hand side, so a second order, sorry, a right-hand side, so a source term, for example. Okay, so now the question is, can we invert somehow my operator? So in order to do that, I'm going to use a very interesting or very important tool, which is I'm going to try to expand capital U in terms of eigenfunctions of the unperturbed operator. So you see that my unperturbed operator, when I take delta to be equal to 0, I recover exactly minus partial Laplacian in x plus v of x. So this operator is completely constant in S. It's invariant in S. And I can study it by doing some Fourier transform in S and some Floquet block in X. If I do this, I can show that its eigenpairs are of this form associated to the above eigenfunctions. So I don't want you to really look at the expression itself. The thing that is important to me here is that these eigenpairs correspond to quasi-momenta which have a very particular form. They start from a point, capital K, and they are on a line that is directed by the vector k hat. K hat, just to recall, it's a transverse direction to the edge. So it depends on R as well. In particular, you see that for commensurate edges, for example, if R is equal to 1, by the way, I haven't included, but this is my point K. So if I look at the line, by periodicity is going to come back to K for commensurate edges. I can do exactly the same thing for another rational edges. And you see that when it starts, it always comes back because of rationality. However, for non-commensurate edges, if I start at K, I never come back to K, but the line which is wrapped in the dual cell, or the dual unit cell, completely fills the cell at some point by density. And this case is precisely the one we are interested in. Okay. So what we know is that our augmented, or what we expect, is that our augmented eigenpair is going to be seeded by the Dirac points. And the Dirac point occurs at these points, which are the high symmetry quasi-momenta and at the Dirac energy. So in some sense, we know that the essence of these eigenpairs are going to come from these points, and all the remaining is going to be somehow negligible. So it seems quite natural to introduce a projection, which here I call a near projection, which localizes a function nearby the high symmetry quasi-momenta and the Dirac energy. And then all the rest, which is in gray, is going to be the far components in some sense. So I don't know if there are, I think there are people who do numerics here. This is very rooted in domain decomposition techniques as well. So we are kind of separating something into two domains here, and we're going to solve and restrict to just one particular domain. Okay. So I can write my corrector in terms of its near components, here pi near applied to u, and the far components pi far applied to u. And then the next thing I want to do is basically rewrite my original equation as a 2x2 linear system, which involve the near components, the far components, in some sense. Okay. So the thing we know is that if all these were real numbers or scalars, one would try to, for example, solve for one unknown in terms of the other, and then substitute everything. And this is exactly what we want to do here as well. For example, we want to solve the second equation in terms of the first, we want to solve the second equation for u far in terms of u near. But in order to do that, we have to make sure that this term right here is invertible. And that's where the first condition I showed you regarding the omnidirectional no-fold comes into play. More precisely, one can show that if this condition holds, then it's actually directly related to the spectrum of the operator on the far components. So if it holds, then it turns out that the spectrum of these parts is bounded away from the Dirac point, and therefore one can show that it's invertible. So in particular, we can solve here for u far in terms of u near, and we get an equation which is reduced now for u near only. So now I'm going just to restrict myself to the near components. And this is where things become very interesting, because you see that my near components is going to satisfy an equation like this. So these are higher order terms which are somehow negligible. I can forget them, but the thing that is important is my operator projected on near components. And if I look at the behavior in the resolvent sense of this operator, one can show the following results. So this is, for example, by using homogenization type techniques or asymptotic analysis, one can show that the resolvent of my operator on near components behaves like a countable or block diagonal Dirac operator. So you have an operator which is block diagonal, and on each component you have a different Dirac operator. One thing that is important here, maybe for the intuition of the proof, is that what happens is that you see we have different stripes, right? We have a countable number of stripes. And what you want to do is you want to somehow localize your components on each of these stripes. And whenever you do that, you get one Dirac operator. So for example, for rational edges, we only have one stripe. If you remember, we only had one near the Dirac point. So in that case, for rational edges, we only have one Dirac operator. But it's completely different from irrational edges, where now we have countably many. So this is going to be an issue because, well, what we want to do is do, again, a second separation. More precisely, I want to look at what happens only in one stripe to reduce myself to just a single Dirac operator. And so what I'm going to do is, again, introduce a second projection which localizes on a single stripe, here in red, and another one which localizes on the other stripes in blue. Okay? And so we want, again, to reformulate the above equation as a 2x2 system and determine for the other stripes, here U0C in terms of U0. But the issue for that is if you want to invert the operator on the other stripes, it turns out that it involves the eigenvalues of the Dirac operators, which form a dense set. So this is once again related to the fact that all these stripes are dense in some sense. So they are arbitrarily close to one another. And so this is, of course, a very technical problem, but the simpler problem I want you to imagine is trying to invert a diagonal infinite matrix where each diagonal elements form a dense set. So suppose that you want to solve this, you want to invert this, this matrix, so sorry. So it's just a diagonal matrix, or an operator on L2 of Z, for example, such that each tau of M is dense in 0, 1. But none of them is equal to 0. Okay, so you want to invert this. Of course, you could simply write the formal expression. You could divide by tau. But because these taus are dense in a set, they can be arbitrarily small. So in general, you won't be able to solve this for any right-hand side. You have to assume, first of all, you have to assume a condition on how fast these tau tend to 0. And then you have to assume another condition on the right-hand side to compensate for the decay. And that's precisely where the Diophantine condition comes into play. So this condition, which is on R, so this is the edge parameter, it tells us precisely how the eigenvalues of the Dirac operators are going to accumulate at 0. So by making this assumption, we can have a lower bound somehow for these accumulation at 0. And by using that, we can control and prove that the operator is invertible. So it's almost over. Now that we have done that, I can restrict myself to the operator just on one stripe. I can expand that operator and show that it involves the beloved, the Dirac operator I showed you at the beginning of the proof. And at this point, it's almost done. Okay? So I could go on and on. So normally this is where the rational case starts, but I won't present that because now I can just bootstrap it. So in particular, one can show by using arguments from previous work that there exists a map which satisfies my equation just on a single stripe. So by doing this, we can conclude and construct our augmented eigenpair. We can also show that it's continuous in S and then take the restriction to obtain the genuine two-dimensional eigenpairs. So in conclusion, I have talked already about these 2 points. I wanted to talk about a few perspectives. One which is a bit dear to me is the case where we want to compute numerically these edge states. So the natural thing you want to do, or the first thing people think about is truncate the domain. You want to truncate your domain in a big enough cell, and you want to compute the eigenvalues and hope for the best. But when you do that, you have spurious eigenvalues that come from the truncation. And because here we have an operator which has dense point spectrum, it's completely a mess because you have the spurious eigenvalues that mix with the genuine eigenvalues. So it's really difficult and challenging to compute these edge states in this particular case. Another case which I would really find interesting to explore as well is the case where the conditions I have presented you do not hold. In particular, the one where the Diophantine condition fails. So in particular, in that case, what I expect based on more explicit models is that the spectrum will be singularly continuous rather than pure points. But to be honest, have no idea on how to prove that. And then it would be also interesting to do the same thing for other types of materials. So think, for example, the Z2 lattice, or even consider nonlinear models. With that, I thank you for your attention. And if you have any question, I would be glad to. Oh, so they will come from the truncation of the problem. So if you, so let me try to illustrate it for the rational case. For the rational case, you will have to solve a problem which is defined an infinite strip. So you want to cut it, for example, here and there. And what you will see is that you have additional eigenvalues corresponding to eigenfunctions that get localized on these truncations. So they are induced by the truncation you make, actually.
But it depends on what boundary conditions you impose.
It depends. So for periodic media, you can show that by choosing your, if you choose your size of periods appropriately, you want to choose it to be a multiple, for example, of the period, and you put periodic boundary conditions, then they won't appear. But of course, these are a posteriori things that have been shown. Here, you don't have periodicity. For the non-commensurate case, you don't have periodicity anymore. So it's no longer clear whether this would work as well.
So are there other situations where we know we have these sort of either the topological defects and that where this would work as well, or it's basically the honeycomb structure and that's it?
No. So I said the honeycomb structure. Indeed, of course, within the honeycomb structure, you have a lot of type of potential you can consider. But you can consider other types of lattices. For example, for the Z2 lattice, you wouldn't have Dirac points. You would have quadratic degeneracies.
Can you still create these kind of modes for such a lattice?
So you could. Technically, you could. And they have been observed experimentally. It's difficult to prove theoretically. The reason for that is, for Dirac points, the effective operator you get is a Dirac operator. For quadratic degeneracies, you get a matrix-valued Schrödinger operator. And for that one, it's rather difficult to see whether it has eigenvalues or not. But if it had eigenvalue, if one could show that, then one could use these arguments as well for non-commensurate edges.